Hello, good evening. Welcome to A Thousand Shimmering Lights, virtual planetarium YouTube show. This is our third one, I think, since moving to YouTube. Uh, so I'm looking at the analytics, and it looks like I'm still the only person here, which is fine because we literally just started. But if anybody does join the stream, I'll just keep an eye on it to see, and we'll get started as soon as we have some people. Let me hop on Facebook and remind everybody that this thing is live now while I wait for more people to show up. For anybody watching this after the fact, because these streams are recorded, oh hey Jonas, what's up? Alright, so got at least one person here. So yeah, just gonna wait for a few more people. I'm gonna make another post on Facebook reminding everybody about it, and then hopefully we'll get started soon. I said, I am live now. Come hang out and talk about space. So, let's see here. Looks like it's jumped up to 2 concurrent viewers. Again, I'm pretty sure I'm one of those. But if anybody is here watching this other than me or Jonas, go ahead and say hi so that I know you're here. It's always good to know people are here. And bear in mind, of course, that I can only share this so far. I can post it to my wall. I can post it to Facebook groups. I need people who are not me to share this with other people. So share the event or just the YouTube link. Let people know this is going on. I do this once a month, and I would like to start getting the word out so that we can have a lot of people joining in, people who maybe are new to astronomy or don't know much about the universe, all different levels of knowledge and experience, to come and learn about everything space, how stars are formed, telescopes, the works. We'll talk about whatever it is. Again, watching the analytics, waiting for some more people to show up. Hopefully we get somebody. But again, for anyone watching this or joining later or what have you, for one thing, I'm getting this thing saying that it's not streaming very smooth. Let me know if it looks good on you guys' end, or if it's choppy, or I need to improve the quality here. I'm not sure what I could do to improve the quality, but let me know if it's not great. But just to let everyone who's here know, the way that this show works is I, of course, have virtual planetarium software open and active, and I can also pull up images on Google. I can pull up images I have on my own computer, whatever we need for visuals. And this is basically the only online planetarium show I know of where you are the planetarium director. So your questions or topics drives what we talk about. So I never plan these things in advance. I don't have any clue what I'm going to be talking about tonight. But I let people ask questions or bring up topics that interest them. Oh, we just had a bit of a jump. I think people are starting to realize that we're live and hop on. So awesome. When you guys join up, just say hi in the chat. Let me know that you're here. Like I said, once we have like maybe 5 or so people that aren't me, we can get this thing going and start talking about something. In the meantime, of course, while we wait for more people, feel free, anyone who's here, to throw something in the chat if there's something you're interested in or a question you have. Now's as good a time as any to remind our viewers that there is no such thing as a dumb or stupid question. A question is simply the state of not knowing a thing and then wanting to know something. So if you ever ask a question from a genuine position of wanting to learn, it is never a dumb question, right? When we do these presentations in person, which thankfully we've started doing, and I will make announcements here in a second about some of the events we have coming up as a club. When we do these events in person, I always love it when children come to them, because children ask those kinds of questions. They ask the questions adults are too scared to ask, or don't think to ask or feel weird asking because they're worried that they'll be perceived as maybe not being informed or what have you. So I want you guys to be like children and ask whatever seemingly dumb question pops into your head, because they're always a great opportunity to learn. Jardine, you're here too. Awesome. Awesome. Fantastic. Yeah, bring everybody. Bring Gabe too, man. So we're just gonna hang out for a couple hours and talk about space. Since I do have a few people here, and since these are pre-recorded and people do watch them later as well on the channel, I'm gonna go ahead and get my opening announcements out of the way. Raw Dust, not sure who that is, but welcome aboard. Uh, I hope it's somebody I don't know yet. That'd be exciting to start getting some strangers in here too, meeting some new people. So I'm going to go ahead and start doing some opening announcements while I let people continue to pour in. So I am David Watley. I am the membership director for the Northeast Florida Astronomical Society. We are the astronomy club here in Jacksonville. So if you live in the Jacksonville or Greater Jacksonville, Northeast Florida area, and you are interested in astronomy and you want to become a member of a club so you can hang out with other like-minded nerds and use telescopes, learn about the universe, pick our brains to become a better observer or astronomer, this is the club. We do have memberships. I'll just go ahead and pull those up real fast. Bear in mind, a lot of the things we do, like this video, are free of charge for the public because we're a 501c3 nonprofit educational organization. Our main goal is just to educate people about the universe. Membership is just one way that people can help support us in that endeavor. But it's not mandatory for any of our events. People are welcome to come. So as you can see on the website, you can always go to nefas.org, NEFAS.org, stands for Northeast Florida Astronomical Society. Go to membership, join NEFAS, you can fill this right out and do the PayPal. And these are the membership levels. So students and seniors are $20, and these are yearly, by the way. This is $20 for a whole year, $40 for an individual, $50 for a family. And then these last two levels are just for people who want to donate extra money to help us in our cause, right? So like corporate sponsorship, that kind of thing. But I didn't come here to be a salesman. I just wanted to give you guys the quick pitch and promote our club real fast and let you know that we are Northeast Florida Astronomical Society. One other quick announcement I want to make is some of the events we have coming up. So we take a quick look at the calendar. We don't have a general meeting this month because of all the people who are going away on vacation, using vacation time they kind of saved up during COVID. But thankfully, because of the lessening restrictions due to the presence of the vaccine and this kind of thing, we do have, I can't believe they're not on the calendar. Okay, I'll bring them up elsewhere here. But we do have some events coming up. One of our events that we actually have two of them on the same day this weekend. Unfortunately, I can't be in two places at once. So I'm only going to go to one of them, and I'll tell you which one it is. But we are doing our usual monthly Hannah Park. Oh, it's Rajesh. What's up, Raj? I should have known that was you because you used that same name. You used the Dust name when we did trivia. So we do have our monthly Hannah Park public observing session. So this Saturday, if you want to come and meet a bunch of crazy cool nerds like me and look through telescopes and learn about the universe and see all kinds of cool stuff and find out more about the equipment that we use, you can come, and you do live in the area, of course. You can come to Hannah Park this Saturday. I want to say the gates are going to be at 7:30, so you want to get in before that. You know what? I'll double check our Facebook group real fast. I'm sure we posted something about it. Give me one quick second because this is important, and I want to make sure I get this information correct for you guys. So let's see here. Okay. What are we doing for Hannah Park? Now, our Hannah Park sessions, I normally do a much shorter in-person version of what I'm doing tonight. I take a laser pointer and I show off all the different constellations and stars and things. But because of our double booking this weekend, I actually won't be at this one at Hannah Park. I'll be at the next event that I'm going to mention here in a second, which you can probably guess because I've got my Google search up right now. But let's see here. Oh, man, this thing got buried. Okay, here we go. According to this announcement, it says 8 p.m. My experience has been that when we do that, They usually close the gate at 7:30. It's $5 to get into the park. We don't charge anything for astronomy. That's just Hannah Park does that. So that's just their fee for their gate. And then they do shut the gates. So if you leave, you can't come back in. So make sure you get in prior to 7:30. We're going to hang out until it gets dark. But that way you are not going to miss out because the gates are one direction after that. The other thing coming up this same Saturday, and I know Rajesh is going to be there. Oh, Susie, hey, I didn't even notice at first that you were here, Susie. Rajesh is going to be joining us as well, and some of our other club members this Saturday at the Museum of Science and History downtown. Again, if you live in the area, let me pull up the events. Okay, here we go. This is the event right here. Rock the Moon, right? Celebrating the moon landing because July 21st is the day they landed on the moon for Apollo 11. It was July 21st, so we're going to be celebrating the moon landing in style. We've got a band coming out. What are their name again? I don't remember what the name of the band is, but there's going to be a band there. They're like an astronomy themed band, so they're going to be doing all kinds of cool songs about outer space and cool stuff like that. So obviously that's going to be awesome. Skyview, that's their name. It's right here on the poster. Skyview is the name of the band. And that's going to be doors at 7:30. The band's going live at 8:30. And then again, just like in Hannah Park, a bunch of us are going to have telescopes set up, and I will be at that one doing my laser pointer tour, so you can get the in-person experience as well. And that should be a ton of fun. Hopefully the weather's going to participate, but rain or shine, we're going to be at both locations. One of our policies is NEFIS never cancels. So if we schedule an event, we are there. So even if it's raining, as long as it's safe to be there, we will be there because people do show up, and we don't need to have a clear sky to talk about space, right? So even if we can't look through telescopes, we always make sure that if people show up, they're not getting nothing, right? So NEFIS never cancels. But especially at this Mosh event, a lot of it's going to be indoors anyway. The concert's indoors, and if we don't have great weather, we're going to set up our telescopes inside so people can come and ask us about them. And again, we'll just talk about space, answer people's questions, and just have a great time. But that being said, tonight we're supposed to hang out and talk about space and have a great time. So let's go ahead and get that started. I'm looking at the chat. I don't have any questions or topics in the chat yet. Again, don't be shy. Don't hesitate. Don't feel like, I don't know if this is a dumb question. Now, Susie says mosquitoes don't like rain. That is true, right? So that's the one plus side. If it's not clear, at least we don't have mosquitoes. Our observing location that we go to, our dark sky location, is out in the middle of the Osceola State Forest by an artificial pond, and man, we get eaten alive out there, but it's worth it. All right, so while you guys think of things you may be curious to talk about, I can go ahead and get us started with a brief sky tour. It's my usual shtick. This is virtual, so I don't have a laser pointer. I have a mouse pointer, which may be even easier for you to see. This software that I use, this is not my software. This is called Stellarium. There are actually two versions of it. Stellarium Web is browser-based, and there's also a downloadable Stellarium that you can get on your computer. It is phenomenal planetarium software made by and for astronomers, so it has all the deep sky objects and everything labeled. You can add the grids for the celestial coordinates, the whole shebang. It's meant for astronomers to use, and it's all free. Completely free. There's also a mobile app that's like $2, but the computer version's free, and Stellarium Web, the browser version I'm using now, is absolutely free, and it is really cool. So one of the cool things it does when you launch it, because it's an astronomy program, is it automatically fast forwards to nighttime. So this is nighttime. This is tonight, actually. This is what the sky would look like tonight, looking to the south. Of course, I can look any direction. I can even time travel in this program. So if we want to talk about something in the winter time, the winter sky, we can do that. Right? We can do whatever we want to do, which is something I can't do in person with my laser pointer. But this is the summer sky. So because this is the summer sky, let's start off talking about something called the summer triangle. So if you guys, after the show tonight, if it's clear, I highly encourage you to go outside and try to find some of the things we talked about. The summer triangle is an asterism that is associated with the summertime. It's something we can easily see in the summer. An asterism is what we call an easily identified pattern of stars that isn't an official constellation. So there's a set of 88 officially named constellations, but just like finding shapes in the clouds, astronomers like to find little patterns and give them nicknames and stuff, and that's what an asterism is. So the summer triangle is just three particularly bright stars in the summer sky. So if you go outside and you look east, right, you'll see it coming up in the east as it gets dark. You will easily see these three bright stars: Deneb, Vega, and Altair. And those three together are the summer triangle. Now, each of those three stars is actually part of a different constellation. So if you found the summer triangle, you have already found three constellations, and I'll show you how to draw those in a second. One thing to note about this software is that all stars in the sky are actually pinpoints. None of them ever looks any bigger than the others. This program uses the size of the dot to symbolically represent its brightness. So the bigger the dot, the brighter that star is. So you can see how bright these three are, especially Vega. Vega is the brightest apparent magnitude, the brightest to your eye of any of them. And we'll actually start with it. So if you find Vega, first of all, if you've ever seen the movie Contact, that's where the aliens come from in Contact. They come from Vega. Excuse the cough. That's my blood pressure meds do that to me. Once you find Vega, you should easily be able to find this triangle shape, right? And then this parallelogram where you've got this pair of stars and this pair of stars, right? So we get this long stretched out parallelogram here, and we have a triangle here, right? Where Vega is the brightest one. That constellation is Lyra the harp. And that represents the harp that Orpheus played in Greek mythology, right? That's Lyra the harp. Now, there is one really cool object to see in Lyra. So if you do have an amateur telescope, oh, and Dennis asks, are those satellites in real time on my screen? Yeah, the web version gives you real-time satellites. Now, mind you, I'm fast-forwarded a little bit right now. This is not the present day, but these are still accurate movements for 10 o'clock tonight, 10:06. This is where these satellites will be. Dennis brought up satellites, so we can talk about those for a second. First of all, we see we got a Starlink coming up, which means we're probably going to have a whole chain of them. If we can look around. No? You don't usually see one by itself, but you would be surprised if you don't ever get out and look up at the sky how often you can see satellites, right? The trick to spotting a satellite is that it will look like a star that just books from one end of the sky to the other, right? And a nice, continuous, steady motion, one end of the sky to the other, and they don't waste time, man. They get over there. Those are satellites, if you ever see those. So I started to mention that if you... Oh, there's another Starlink. Okay, they're out here. If you see Lyra the harp, and you do have an amateur telescope, one little trick is to point your telescope right between these two stars, Sheliak and Sulafat. If you look about halfway between them, there is this object here called the Ring Nebula. And I can pull up an image of the Ring Nebula so you guys can get a good look at what that looks like. And it is a class of object that we call a planetary nebula. And again, as we discuss this stuff, feel free to ask any questions you have. That's the Ring Nebula, right? So what it is the way a star ends its life depends on its mass. So the big stars explode catastrophically and they leave behind what we call supernova remnants. The medium-sized stars around the size of the sun, for example, the sun would do this, they don't die violent deaths. Instead, they sort of puff out and they blow out the outer layers and they leave behind this little chunk of carbon where the core of the star was. It's all that's left is the core. The rest of the star is just expanding out in this three-dimensional sphere of glowing ionized gas. And that's why planetary nebulae have these sort of spherical shapes, like you see here. And if you look, you see a little dot in the middle. That is that little core, that leftover core. That's basically a chunk of carbon, oxygen, nitrogen, practically a literal diamond in the sky, about the size of the Earth ish, and they glow from leftover heat. They're actually no longer active stars. They just glow because they're so hot, and that they will have to radiate away that heat over a very, very long time. And we call that a white dwarf because it's a very small white star. Eventually, every white dwarf cools off and it goes out, it stops glowing, and we call that a black dwarf. And what's interesting is we actually know. Oh, I just noticed that Jonas, yes, this does actually. You could program Stellarium for your particular location, which means that not only can I time travel, I can also travel to the southern hemisphere. If we want to look at things in the southern hemisphere, we can go to Australia and see Australia's sky. Um, but what I was saying is we can know to the exact number how many black dwarf stars there are in the universe, because that number is zero. Actually, the universe isn't old enough for any of these stars to have cooled off sufficiently to stop glowing. That's how long it takes for them to cool off. Is it takes longer than the universe is old, by a wide margin. In reality, it would be a long time in the future before these stars start winking out. So that's the planetary nebula. They have nothing to do with planets. I think it's the dumbest name ever, but we're stuck with it, so that's what it is. And that's something that you can easily find right there in the constellation Lyra. And again, I'll zoom back out again. The way to find it, get rid of the lines a little bit because they're distracting. Find the three bright stars. The brightest star, you get the triangle there, and then you get that parallelogram. And halfway between Chelyabinsk and Sulfat, that's where it lives, right here, Ring Nebula. It's a little bit less than halfway, but if you put your telescope halfway, you're usually going to get a piece of sky about this big anyway, and you might have to adjust slightly, but it's basically halfway. It's the easiest way to find it. That's not the only thing over here in the Summer Triangle, though. We do have this star Deneb, and Deneb is actually part of a larger constellation as well. We can draw out to Sadr, and then to this star, which Stellarium is calling Gaia, but everyone I know calls this Alberio. And in fact, even if I zoom in on it, I think it's going to put the word Alberio there. So I don't know why it says Gaia up here. But we all call that Alberio. Right? So we get that line, and then we can draw this line across from Delta Cygni to Epsilon Cygni. Right? And we get something, this is another asterism, not a true constellation, but people call this the Northern Cross. We call it the Northern Cross because there is a constellation called Crux, which is also known as the Southern Cross. It's near the celestial South Pole, so you have to get to the Southern Hemisphere or near the equator to see it. But this is our Northern Hemisphere cross in the sky, so some people call this the Northern Cross. If we extend the arms of the cross down to these stars here, Theta, Iota, and Kappa on one side, and then if we come down to Epsilon, to Zeta, is this part of it? Yeah, to Mu on the other, we get this sort of swooping on both sides, because what this actually is this is a swan. It's got a wing over here, a wing over here. Deneb is where the tail feathers are, and the swan's beak is Alberio, the star up here, so it's got the long neck. If I add in the lines, you can easily see that. If I add in the artwork, it becomes really apparent that Cygnus is a swan. So that's another great constellation. There's a couple of really cool things. You'll notice that there's something circled here already. If I zoom in on that, this is called the North America Nebula because it looks like North America. Imagine it rotated to the side, right? And we're about here. This is Florida, right? This piece right here is supposed to resemble Florida. I want to say this guy over here is called the Pelican Nebula. It's another piece of gas. So that's a cool thing to look at in this piece of sky. And then if we move over to the third star of the Summer Triangle, there's one more constellation to see here. So, for one thing, we've got Tarazed, Altair, and Alshine, right? These three stars. And I want you to imagine that that's like the head and beak of an eagle, like in profile, just like you'd see them on a quarter, right? And then, except I think traditionally this would have been like a Greek constellation, so not a bald eagle, but like a golden eagle. Because if we come down, we've got his body somewhere around here, around Delta. And then up to these stars here, we have one wing. Oh, that's actually part of Hercules there. That's not it. And then if we swing up to these stars here, Eta and Theta, we've got the other wing, and then his tail feathers, we kind of just have to fill them in with our imagination. So we see there, that's, okay, the artist drew his head up here. I've always imagined these stars are his head and beak, but that's all subjective, I guess. But that's a quill of the eagle. Now, one interesting thing is this star is called Altair, but anyone who's played the Assassin's Creed games knows that that's an Arabic name, and it really should be pronounced Altair. And if you've played Assassin's Creed, you know that your character in that game is very much associated with eagles, right? You climb up the buildings and you get the eagle vision, and you do the eagle thing where you jump off the leap of faith, the eagle flies around. There's a whole eagle theme. And so sure enough, there's an eagle constellation, and Altair is one of the stars in that constellation. And speaking of, you might have noticed by now that several of these stars have Arabic-sounding names, right? We've got Tarazed, Altair, Al-Sha'in. We've got Vega, not so much. That's more Greek, but what are some of the other ones here? Sheliak, Sulafat, right? These are all Arabic names. Sadr, right? Sadr. I feel like somebody even told me what that means in Arabic, and I've blanked on it. But at any rate, these all, and actually Deneb too, by the way. Deneb comes from an Arabic root that means tail, and there are actually several different stars that are the tail of whatever constellation that have Deneb in their name. So the tail of Leo is Denebula, which is the tail of the lion, right? So the reason why there are so many stars with, Alderamin, there's another one right there. The reason why there are so many stars with Arabic names is because there was this period in, someone mentioned the Veil Nebula. Yeah, we'll talk about that in a second. There was this period in the Middle Ages where the Islamic world, the Middle East world, was having like their big golden age, right? And there were all these Arabic scholars, and people would literally travel to Saudi Arabia, Egypt, these places to study with these scholars, and it was like this big resurgence, right? This is where algebra was invented by a man named Al-Khwarizmi, and he wrote this book, Al-Jabr, this, whatever, I forget the name, but it means like on the solving of equations, etc., etc. But that's where we get the word algebra, and from his name we get the word algorithm, right? So there were also a lot of astronomers at that time. And actually, there was a lot of overlap in the Middle Ages between astronomy and math. A lot of people that were into math were into astronomy and vice versa. So this is when these Arabic astronomers just went on a naming bonanza and just named so many stars. So we have a ton of, like, a lot of the constellations we got from ancient Greece, and they have Greek names. They do have other names in Arabic, but a lot of the names of specific individual stars, especially the ones that aren't the really bright ones that we already got names for from the Greeks, have Arabic names because the Arabs actually got to name those. One other interesting thing about this Stellarium software, I don't think the web-based version does this, but the downloaded version, which is also free, actually has an option where you can go in and swap out the star lore for other cultures. And you can actually see the Arabic constellations or the ancient Chinese constellations, right? And see different constellations for different cultures throughout history, which is really cool. And I like to, when I can, give shout outs to some of the other cultures besides just the Greeks, right? Because we get a lot of Greek stuff when we learn about space, but every culture has found interesting stuff up here. So somebody mentioned the Veil Nebula. Now, the Veil Nebula is cool, and it lives about here-ish, right? On the bottom or right-hand wing of Cygnus. And you'll see it takes up a lot of real estate, actually. So if you point a telescope at this, you sometimes will only see part of it. You have to move your scope around to see the whole thing. So what this nebula is I mentioned before how some stars die gently and they puff out their outer layers and become what we call a planetary nebula. But the big stars don't go gentle into that good night, right? They detonate. They explode huge. And they just get shredded and they throw their guts everywhere. And that's what we're seeing here. This is this supernova would have exploded a long time ago because we can see how far this has drifted, right? It's all sort of drifted apart and it's sort of tenuous and broken up. So this is something that exploded a while back. But that's what you get when something explodes, and so that's what this actually is. And so you'll see that there's a bit of it here. There's a bit of it over here. This part is, gosh, what do we call this? The West Veil Nebula? What direction is this? That's east. Okay, so that's the East Veil Nebula, right? Is this bottom part here. And some people call it the claw because it almost looks like there's like a hand here, like a claw like this. And then you have the West Veil Nebula, which is this object that people often call the Witch's Broom. And this thing looks awesome through a telescope. There's a really bright star here, 52 Cygni, and it looks like it's embedded in this gas and lighting it up, but it's actually coincidence. That star is not related to that gas at all. It just happens to line up like that, and it looks really, really cool. In fact, if you guys look at the logo for my YouTube channel, my logo is actually a sketch I made of this part of the Veil Nebula with that star in it. Everything in my sketch looks kind of teal because the filter I use does that to it. It turns it kind of teal. Another feature that's a little harder to see unless you have a bigger telescope or you're very patient is this region called Pickering's Triangle. It's another really cool thing to find here in the Veil Nebula. So Veil Nebula is a very cool feature of constellation Cygnus, and it's the shredded up leftover guts of a detonated star. And it looks like we got Scott there. Jonas asks, what is the average, or is there an average lifespan of a star? That's the kind of question I'm talking about. That's a great question. So the lifespan of a star depends entirely on its mass. And the relationship is actually backwards of what you might think. The bigger stars actually don't last very long. So some of the really, really big stars can have lives in the millions of years, right? A few million years if they're really huge. The smaller stars can have lifespans. The really small ones can have lifespans all the way up to trillions of years. But usually a lot of the stars in the sort of the mid-range, since you were asking about an average, will have a lifespan of a few billion to maybe hundreds of billions of years. Our sun, if we want to use our sun as an example of a fairly middle-of-the-road star, our sun's lifespan is about 10 billion years, and we're about halfway through it. So the way to think about stars and their lifespan is that the big stars are like SUVs, right? They have a bigger gas tank, but they have terrible fuel economy, right? They just eat through their fuel very, very quickly. And that's because those big stars get super hot. They just burn really, really hot. And it's not really burning. We call it burning, but it's fusion. It's a fusion reaction. But that reaction is sped up by the immense heat and pressure of that gigantic star. So it's going to eat through all the hydrogen in the core much quicker than a smaller star that, even though it doesn't have as much hydrogen, is just very slowly going through its fusion. And it's not, it's hot. Like you'd incinerate instantly, but on a scale of stars, we would say that it's cooler, right? There's a class of stars that we call red dwarfs, and they're very small, very cold, relatively cool red stars, and they also become black dwarfs. They actually don't explode or become planetary nebula. The prediction is that when those guys finish up their fuel, they just wink out. The problem is that those tiny little red dwarfs have lifespans literally measured in trillions of years, and the universe is only 13 billion years old. So those little red dwarfs, like literally all the stars in the universe will die, explode, new stars form, die, explode, new stars die, explode, whole generations, material used up, the universe goes dark, and those little guys will still be going for epochs beyond that before they finally wink out. It's incredible. There's a star in the Milky Way that is believed to not be an original member of the Milky Way. We must have captured it at some point because it's older than the Milky Way galaxy. And it's actually in a globular cluster, and it's older than all the stars in that cluster. And it's one of these little red guys, and it's literally like the universe is 13 billion years old. This thing, the universe is like 13.5 billion years old. This thing's like 13.2 billion years old. It's almost as old as the universe itself and still going strong. So they call it the Methuselah star. So yeah, it's actually really cool. And actually, I'll go ahead and bring this up in my visuals here on Google. There is a very simple simple equation that you can use to determine the lifespan of a star. Let's see, calculate star lifetime, right? Main sequence lifetime. Here we go. I think is this the one I've used before? Yeah, so this formula, because stars actually obey very straightforward, well understood laws of physics, right? So this is why some people say, like, oh, how do we know they're going to live that long if we haven't watched them? And the answer is because if they don't, then we don't know anything about physics, right? Because if anything we know about physics is right, then we definitely know how long these stars live because they have to. The laws of physics require it. Is this the... I found a website one time where you can literally plug in the mass of a star and it will spit out the answer. It will tell you how long it will live. But this one is not it. But you can Google that on your own. But it really is that easy. And so if we know the mass of a star, and there's ways to determine a star's mass, you can measure that based on how it interacts with other objects and that kind of thing. Based on its light, you figure out how big it is. And then you can easily just plug in and figure out how long it has to live. And since that's also based on the fuel efficiency, how long it takes for it to eat up all of its fuel, you can then look at the chemical composition of the star, the percentages, and figure out how old it already is, right? So it's actually interesting how straightforward it is with stars to figure out how long will this star live and how long has it lived, right? That's why we know the sun's lifespan is about 10 billion and it's about 5 billion years old. Part of that we know because the Earth is about 4.6 billion years old, and obviously the Earth is not older than the sun, right? So that's part of it too. But we can look at the amount of hydrogen and the amount of helium in the core of the sun and calculate its current age and figure out how far into this process it is. So actually, let's talk about that for a second. So what actually powers a star? This is what I was talking about earlier. I have no idea what I was going to talk about this, but the questions just kind of lead me there. Plus, it's one of my favorite topics, though. What powers a star is that it's basically just a big ball of hydrogen, right? And its own weight, its own mass crushing in on it, heats it up. And a star, when it's first forming, gets hot enough that nuclear fusion becomes possible. So you have these little, you know how an atom has a nucleus and it has the electrons going around. It's too hot to hold on to the electrons. They're just gone. And all you have is the nucleus. Now, a hydrogen nucleus is literally just a proton, right? Sometimes you'll have one or two neutrons, but usually just a proton, right? But those three forms are inside of a star. And so the star will take two hydrogen nuclei, so usually just two protons, and it does a chain reaction with them where it combines them. And what you end up with at the end of the process is two protons and two neutrons combined, right? And that's a helium nucleus. And when that happens, it gives off heat and light. And that heat and light is what powers a star. Because as the star is living, its own gravity, its own mass, is always trying to collapse it, to crush it down to nothing. But the outward force of the nuclear reaction is always trying to blow it up, right? So every star is trying to implode and explode all the time. And the equilibrium between those two allows a star to just be a ball, right? It's a sphere. When the star runs out of hydrogen and it's turned it all into helium, that's when the core begins to collapse, and that's when we start to be at the end of the star's life. But during that whole time it's turning hydrogen into helium, we say that the star is in its main sequence life. And the reason why we call it that, I'll go ahead and bring up the Hertzsprung-Russell diagram. I guess it was a matter of time. The HR diagram here. So I'll find a simple version of it that's a little clearer, because actually the real diagram is a bit more complex. But this is the Hertzsprung-Russell diagram. I want to take this moment to remind everybody that we are a 501c3 nonprofit, and that I am also just acting as myself, not the club. And we don't own any of these images, but we're also not monetizing this video. Don't sue us. So this is the Hertzsprung-Russell diagram. And the way that you read this diagram is on the left-hand side is how bright a star is, and across the bottom is how hot the star is, with the hottest stars on the left-hand side, and they are blue in color, and the coolest stars are on the right-hand side, and they are red in color. And the vast majority of stars fall along this curve. And so that's what we call the main sequence. The stars in these other little groupings that have been given cool names are rarer. And there's a reason for that. And that's because any given star will spend most of its time somewhere on this line, right? So the sun might be here, this little yellow guy, right? Or probably more like close to the white part of yellow. But this is the main sequence. And so a star comes alive and it spends its time on the main sequence. It's a steady color and temperature and size and brightness for most of its life. So that's why we call it the main sequence life. What happens is when the core runs out of hydrogen, it begins to collapse because it's not generating that outward energy, that outward force of expansion from that nuclear reaction. Now, a star is so big, it doesn't collapse all at once. It's not a solid object. So the core is going to collapse in, but the outer layers take a little longer, right? Because the closer you are to the middle, the more gravity you feel, the more you're accelerated in. So that core collapses on itself. And then what it will do is it will generate heat because of the collapse. And now it will take the helium that it made, which is basically the ashes of the first burning process of the main life, and it will turn helium into heavier elements, right? We get like carbon, we get oxygen, nitrogen, these kinds of things. Then the rest of what happens depends on the mass of the star. But that fusion will cause it to expand, and it happens all kind of very rapidly, so it really causes expansion. But the outer layers of the star, as they expand, any gas that expands cools down. So if you've ever used compressed air on your computer, you notice the bottle gets cold. That's because the air expands, so it has to get cold, right? Anything that expands gets cold. So the star, as the outer layers expand, they cool off and they turn red. And that's where we get the red giant and red supergiant groups here on this chart, right? Medium-sized stars, they tend to become red giants. The really big guys become red supergiants. Blue giants are kind of a special thing, but they're like their thing. So, and I'm trying to keep this a little bit simple. But they swell up and they turn red. So there are red stars that are just red. Those little red dwarfs I mentioned, but you don't really see those naked eye in the sky. So when you're looking at the sky with your naked eye and you see a red star, that star is dying, right? That's what that means. That's a dying star. So for an example, I can actually show you here in Stellarium some examples of big red giant dying stars. And a really good example is this guy, Antares, right? Again, this is tonight's sky. You can actually find this in the sky tonight, and I'll talk a little bit about these constellations, but I'm really excited to wrap up talking about star death because I find it to be a really cool topic that seems to always come up. But Antares is dying, right? It's a dying star. You'll see here in Stellarium, it says it's actually a double or multiple star. If we really zoom in on it, it actually has friends. But Antares itself is dying, and so it's this reddish color. And this is not just the software. You get outside and you look up, it looks red. In fact, it looks so red that it kind of looks like Mars. And Antares actually comes from the Latin anti and Ares. Ares being the Latin name for Mars, or the Greek name for what the Latins called Mars. So not only is the star not Mars, but its name is literally rival of Mars, because it's red like Mars. But I always like to joke around that not only is that not Mars, but its name literally means not Mars. But really it's more like rival to Mars, because it looks so much like Mars. But that's a red giant star. That's a dying star. And then I already mentioned what happens after that. The medium-sized stars will do several rounds of collapse and expansion as they generate these little bursts of energy that allow them to fuse the helium. And all the while, they're puffing out the outer layers, and then you get, like, the ring nebula that I mentioned, the planetary nebula. The big ones will do these successive collapse and expand and collapse and expand inside the core, but what happens every time is they keep jumping up to higher and higher parts of the periodic table. They're fusing heavier and heavier elements, and you'll get these shells, these concentric, like, spheres, like an onion inside the star, where the core is fusing. Gosh, I don't know all the ones that they actually do, but it's using something really heavy, and then you got gold outside of that, and then you've got whatever, and you've got carbon, whatever, and then you have a layer of hydrogen being turned into helium because, believe it or not, there's still hydrogen in a star that's dying because it only can do fusion at the core, right? So the stars actually die with unspent fuel. But you get all these layers. I mean, the really big stars, what ends up happening is the core of the star is fusing the heaviest thing, and all the layers build up. And this energy is making it nice and huge and red and awesome. And then the core will start the process of making iron, right? So it's going to fuse things together to make iron. This is where we get, by the way, this is where we get everything that isn't hydrogen, right? The universe was all hydrogen. Stars had to make everything else. But it's making iron in the core. And the problem with iron is that all these reactions require energy to get going, right? You need to heat them up to get the reaction to go. But you get back more energy released in the form of radiation and this kind of thing than went into it. It's a net gain, right? Just like when you burn gasoline, you have to apply a spark. You need a little energy, but then you get the explosion that drives the piston. You get more energy out than you put in. Well, iron is terrible fuel, right? The reaction that, well, actually iron's not the fuel, but the thing that gets turned into iron, right? That reaction that makes iron actually requires more energy than you get back. And so it steals energy from the star rather than giving the star energy. And that is not a sustainable condition at all. And so when these really, really big stars form iron, they don't get that outward force of the energy coming off of that fusion reaction, and the whole thing just collapses all at once, right? It just all collapses at once, and then that collapse does one more incredibly energetic fusion reaction, and it will literally jump up to like uranium, I think. I have to look it up. But it will fuse some really heavy stuff all at once, release a ton of energy all at once, and they just detonate. They just go off. So, what this means is that for the big stars, iron is star poison. It really is. Every piece of iron you've ever encountered in your life, the iron in your blood, the iron in your cast iron skillet, killed a star. Every last atom of iron was responsible for the death of some big star. And now it's part of you. And I think that's really, really cool. But that's an exhaustive answer, probably way more than you meant when you asked how long do they live. But that's an explanation of not only how long do they live, but how they die. Because it is really interesting to learn how these stars die, right? And so if we bring it back to stellarium and look at what's in the sky tonight, again, if you have an amateur telescope, or if, like some of the people in the chat, you live in this house with me, then you can see tonight, if it's clear, some examples. You can see over here near Vega, this ring nebula, which I can pull that back up for you guys again. The ring nebula is an example of a medium-sized star that died the more gentle death. Right? That's the fate of the sun. That's what's going to happen to the sun in about 5 billion years. We're going to get one of these, right? I can show you a couple more examples because they don't all look exactly like that of different planetary nebula. We've got the blue snowball is another good example. No, oh goodness, nebula. Right, this little fuzzy guy. That's the blue snowball. A really good one that people like is the Helix Nebula. You'll sometimes hear people call this the Eye of God because it looks very much like an eye. It just has that look, right? So this is the Helix Nebula, right? Very similar to the Ring Nebula. A little bit more stretched out on the ends. What are some other really good examples? Ant Nebula. Right, this one's crazy looking because it formed two lobes, right? This one formed like two lobes shooting out this way as it died, right? This one's like in the process of doing that expansion thing that I was talking about. So these are all planetary nebula. Oh, another one, Dumbbell Nebula. This one's actually in the sky tonight. I'll show you where this one is, right? This is another one. You can find a better picture than that. Okay. Sometimes you have to be careful with some of these pictures. Like, this is not invisible light. This is some other spectrum. I'm not sure how they got it to look all green like that, but yeah, that's like X-rays, right? So it's not always the case. That's what it looks like. This is kind of what it looks like, right? Expanding sphere of gas. We call it the Dumbbell Nebula because we got this sort of like hourglass shape in it. These are all examples of that planetary nebula, that star that just goes and puffs out its outer layers. Some examples of a star that's exploded. Okay, there's a great question about stellarium and the path of an object, so I'll wrap this up real fast and address that for Jane. So to give you a couple of examples of stars that went supernova and exploded, because that's what that's called, by the way, that's a supernova. We can look at supernova remnants. We already talked about one of them called the Veil Nebula, right? And again, you see a lot of pictures of like just the pieces of it because it's so big, but here it is all together. You can see how it's all ripped up, and I mentioned before it's very much kind of drifted apart. We want to see a younger one that hasn't yet sort of faded, as it were. We can look at the Crab Nebula, right? The Crab Nebula is cool because if you dig through old like Chinese astronomical records, there's a record of when this thing exploded. People saw this in the sky. It looked like a new star, and they wrote it down. We actually know exactly when this star blew up because the ancient astronomers actually recorded it happening. It blew their minds. They had no idea what was happening. There was a new star, then it was gone, and now this is what we see when we look there. Look how shredded up that is. Man, that thing just went off back in like, what was it, like the 1200s or something, right? It's just, actually we can find out. 1054. It was year 1054 is when that thing went off. And it still looks like this, right? So that's really cool. So, all right, addressing the chat, because like I said, the whole point of this is I answer you guys' questions. Yeah, Scott mentioned the Owl Nebula. That's another wonderful planetary nebula. It's got two little holes in it. Looks like an owl. So Jane asks, maybe this is out of the scope. First of all, pun intended, I hope. Can stellarium show the path of an object, such as Venus, over the course of time, such as centuries, while displaying the path? So it won't show like a line, but you can find Venus at any given point, right? Because stellarium software, any planetarium software that's worth its salt, will let you time travel, right? So if we if we can, and I can actually delete the Earth, bloop, there it goes. And if we find the sun, there's Venus, right? Right by the sun. So I can time travel, and I'm actually going to time travel by years, right? You see the planets all orbiting around the sun, right? 2044, where's Venus going to be at exactly 2242 on, July 15th in the year 2044? It's going to be exactly there, right? Because the cool thing about the planets is they move in very predictable ways. So we can predict, and if I was really feeling crazy and if the software would let me, I don't know if I can edit this. No, I can't. I'd have to click the button a ton of times, but we could go to like 4078, put in a day, time, location, and see that exact sky, right? But to answer your question, at least the web-based version doesn't put like a line to show it, but you will find its location at different points in time. And you could do that for literally any object. I'm going to time travel back to the present day. All right, there we go. And I'm going to put the Earth back in place. I do like that if you look down, the Earth becomes transparent. So that's how we can time travel. And you can predict where these objects are going to be. You can predict eclipses, right? And the reason why this is a big deal in science, we can make predictions to find out if our model is correct, right? If we think we understand how it works, we go, if that's the case, then this should be the case. And the better you're able to make predictions and the more accurate those predictions, that means that you have a good model, right? So The point of this channel is to be just an educational channel. It's not meant to be the flat earth debate channel, but I will say this. We can predict things like solar eclipses, right? Me and my dad went to South Carolina back in 2018. We went to a particular spot, looked up at a specific time, and we saw the sun get blotted out. Because the model is true. It really is the case that the planets orbit the sun and the moon is orbiting the earth and the earth is not flat, right? Because these things are true, we can make these predictions. So as much as, like I said, you see these YouTube channels where they're like, oh, well, I'm going to look out over this lake and that mountain should be a little bit taller if the earth is flat, whatever, does it match the measurements? And of course, if you do the math, it does work, but just go see an eclipse, right? How'd you know where to go and when to go? Because the model's right, because it's true, right? But again, not my point to be the Flat Earth Debate channel. It looks like the chat disconnected and reconnected. How is the broadcast for you guys? Am I still coming through nice and clear? Are you guys having any difficulty with it? Or is it like real choppy? Well, again, I'm not sure if there's any way in the middle of a stream for me to improve it, but let me know if we're struggling right now. And if you are still here, maybe say hi or something and let me know that you're still here. Because on my end, the chat disconnected and then reconnected. So I just want to make sure I didn't lose people. Jane says perfectly clear. Cool. All right. So hopefully you guys are still there, still with me, still curious and asking your questions. Simon's there. Awesome. All right. So Simon, another hour. Appreciate you being so patient with me. So, all right. What else can we talk about? So, again, since I've addressed all the questions in the chat, I might as well come over and go back to my tour of the sky and what we can see in the sky tonight. When you found the summer triangle, like I mentioned, there's several constellations. If I add the lines, there's actually even more constellations you can find using that triangle, right? So once you find Albireo and Altair, you could find these two constellations, Vulpecula and Sagitta, between them. There's supposed to be a fox and an arrow. They're lines. But, Delphinus is here. There's a lot of cool stuff. I mentioned that Dumbbell Nebula earlier, by the way. If we take this star, Epsilon Cygni, and let me get rid of the art. Okay. If we take Epsilon Cygni to solder to Albireo, and then we imagine where we would need to add a star to make a rectangle, that is where we find the Dumbbell Nebula, if you are curious to try and go after it tonight, right? That's where you would go for it. The Dumbbell and the Ring Nebula that I've mentioned so far are fairly bright, not terribly difficult objects in terms of deep sky. They're not like planets, but in terms of things outside the solar system, they're kind of on the beginner mode, right? They're not as hard as some of the other objects. They're a little bit more friendly to urban skies would be a challenge, but suburban skies, you could probably still see them a little bit. They'd be a little faint, right? So those are good ones to go after if you're new, and they're going to be in the sky tonight. In addition to the summer triangle, another really, really prominent thing associated with summertime is the constellation Scorpius and its companion Sagittarius, right? So if we look to the south, the easiest way to find this one, and you'll see how bright all these dots are. See how big the dots are? These are bright stars, right? I've spotted this from Jacksonville, right, downtown. So this is not a faint, difficult constellation. If you look up and you see these three stars, right, they're slightly bent, and you'll see this red one in the middle. That's Antares. As you can see, by the way, M4 is right here. You notice how the software is letting me know there's cool things I can look at. So we get this one little curve like this, and then we've got Acrob, Jashuba, and Pi Scorpii forming a second curve like this, right? Very slightly bent, 3 stars, 3 stars. That's the easiest way to find Scorpius. Once you find it, the curve that has Antares, you can start tracing that down away from the other curve, and then you can just keep going to star, to star, to star, and it will loop around, come back, and then make a very sharp angle. So what this is, those two sets of 3 stars, personally, this is how I draw the picture. It's all imagination. But I just imagine a big blurb around all of that, and that is like the torso of the scorpion, right? It's just sort of, I just incorporate all those stars. I imagine his pincers are out here. There's no stars for them. I just sort of fill them in with my imagination. And then everyone agrees that when you come down and you whip around, this is the tail and the stinger, right? That's the stinger right there. This is Scorpius the Scorpion, and I'll add the lines, and you'll see it there. Of course, add the artwork, and this artist has chosen to interpret these 3 stars as one of the claws. I guess it's an equally valid interpretation. He's got his stinger going this way. I don't know why you wouldn't use the silver nugget cluster, which there's actually a star here. Hold up. I'm not selecting the star. There we go. I don't know why you would use G Scorpii as the stinger's tip, but that's, again, personal preference, I guess. But that's Scorpius the Scorpion. All right, really cool constellation to find. It's got a great example of a naked eye red giant star, so you can see what a dying star looks like. And then if we look to the left of it, we get this shape. Now, I'm going to add the lines to make it a little bit clearer. This is supposed to be a centaur, but I think it's a teapot. And that's what we all call it. Everyone knows to find Sagittarius as a teapot. These stars are really bright. There's been nights where I can't see anything else, and I'll look up and I'll just see a teapot. And I know Sagittarius is there, right? So we can see the body, right? I'm a little teapot, short and stout. Here is the handle. And here is the spout over here, all the way to Al-Nasi, where you would pour out the tea, and Caus Borealis forms the lid, right? The lid for the pot. That's the Sagittarius constellation. Now, Sagittarius and Scorpius are really cool because if you look in the software, they lie on the biggest, fattest, brightest part of the Milky Way, right? So, the Milky Way is a flat spinning disk of stars, right? If you guys don't know, I can pull up an image if you guys want to see an image, but basically it's a big swirling, it's one of those big spiral galaxies, right? And again, if you're not familiar with that, we can talk a little bit more about that. So when you look up at the night sky and you see that bright smear across the sky, which you have to get out somewhere really dark to see it, right? You won't see it from the city. I have seen it from some of the darker parts of like Orange Park and Middleburg. You'll see it very faintly. If you get out somewhere dark, you'll really see it. That's the Milky Way, but what that is we're embedded inside the Frisbee, basically, looking through it. And as we're looking through a flat disk, it looks like a line from the Earth. But in reality, we're actually embedded in a disk. Now, we don't live in the middle of the Mercury, in the middle of the Milky Way, right? Imagine my hand is the disk of the galaxy. Actually, I'm going to hop over to the real time so I can see this. Imagine my hand is the disk of the galaxy. This is where the core is. We live like here, and actually if I open my fingers, right, maybe bend them slightly to represent the spiral arms, we live just inside of like one of the outer arms, right? Almost in the gap between 2 of them, but out near the edge. So, when we look up at the Milky Way at different times of the year, we're always looking away from the sun. Right? So as we orbit the sun, our window on the universe is going to shift and it's going to turn, and we see different directions depending on the time of year. With me so far? Makes sense? So, if I go back to my example of a flat disk, sometimes we're looking out this way, and then sometimes we come around in the orbit and we can look through the whole hand, right? So that's why the Milky Way looks different in the summertime than in the wintertime. Because it happens to be that when we are having summer in the northern hemisphere, we're at a spot in our orbit where the northern hemisphere can look and see right through the galaxy, right? If you're in the southern hemisphere, that would be wintertime is when you can do that. As we're looking through the middle, we're looking through all the whole rest of the galaxy and the core, the thickest parts. And so, in the sky, it's going to be particularly big, particularly bright, particularly wide, right? And it happens to be that Sagittarius's teapot spout points, and actually this star right here, 3 Sagittarii, is almost bang on dead center for the core of the galaxy. Now, the Milky Way is shaped if you look at it from the side, it's almost like a flying saucer. You got the little thing right here, and then it's got a bulge. It bulges in the middle, right? It's got like a bubble. So we can see that. We can see that, it's about this wide here, and then it opens out to this wide, right? So that's that bulge in the middle of the Milky Way, and you can see that in the sky. If you get out somewhere dark, you'll see it opens up, and then you'll see it shrinks back down on the other side. There's a supermassive black hole right here called Sagittarius A star because it's found near Sagittarius, or you have to look through Sagittarius to look at it. Is what I should say, because these objects are not a nice flat picture like we see them. Some stars are close, some are far. It just forms a picture from the perspective of the Earth. But that's the cool thing about the summer. And then in the winter time, we're looking out through the last little bits of the arm that we're a part of, and then out into deep space. So if I time travel for you, so this is what the Milky Way looks like if you go somewhere really, really dark in the summer. Delete the lines for a second. Delete the atmosphere. Oh, there we go, right? You won't get the color like this without like long exposure photography, but you'll definitely see if you come out somewhere dark like our observing location, you'll see these dark patches, actually. You'll see these places where gas and dust is blocking the light. It really is that rich and that detailed. But if I time travel to like, say, February or January, this is what the winter Milky Way looks like. And this is actually, again, naked eye, it wouldn't be this bright, right? It would be very faint, very subtle, and it actually gives out entirely right around Perseus here, right? So that's us looking out through the edge. So if you want to plan a trip out to somewhere really dark, and it's important to you that you want to get a look at the Milky Way, July is your time to do it, right? July, August, June, July, August, that time of year is the best time of year to get out and see the Milky Way because it's going to be big and bright and beautiful. Now, personally, I love both of them, right? For sentimental reasons. I can appreciate the beauty of the faint, subtle, tenuous winter Milky Way. But if I'm being honest, it is brighter and it is bigger and it is more impressive in the summertime. I've just learned to appreciate the subtlety and the bombastic thing. I think they're both beautiful in their own way, right? And it's like a parent with their children. I love all of you equally, especially him. All right, so that is Sagittarius, though. That's how we find Sagittarius. And once you found Sagittarius and Scorpius, you know you're looking near the center of the Milky Way. Now, Sagittarius is a landmark to find a lot of cool deep sky objects. Susie says that she's on YouTube. Yeah, I'm just doing YouTube now. I was doing Twitch before, but I found that like people had to join Twitch and whatever. But by doing YouTube, like anyone with a Gmail address can participate in the chat. So, yeah. And so Richard's confirming for us in the chat that the Milky Way looked awesome the last time they went out to observe. Man, I kind of had, I don't know what I was doing Monday, actually. I was probably doing nothing important, but I wish I'd joined you guys out there because it was apparently a great night. And I do miss getting out there under that dark sky. But yeah, so Sagittarius is also useful to find other cool objects. If we imagine Sagittarius as a teapot, and we imagine it starts steaming, we follow that trail of steam up and back, right? Just imagine this with your mind's eye. There's a lot of cool things to see along the steam trail. Now, some of this stuff, if you get out somewhere dark enough, you'll see little blurry patches. And if you point your telescope, you'll see cool stuff. Right? So a good example is M8. Now, unfortunately, the web-based Stellarium images are not awesome, to be perfectly honest. So I'll be bringing some of this stuff up in Google. But that is the Lagoon Nebula. Lagoon Nebula is one of my favorite nebulae. It is really cool. Really, really cool. The Orion Nebula gets all the press. It's a wintertime object, and I love the winter because of some of the cool stuff. But look at this guy. This is the Lagoon Nebula. Not quite as big and bright and obvious as the Orion Nebula. It needs a dark sky, but it is worth it. Now, again, this is a long exposure photograph, so we have to temper our expectation a little bit. If you're looking at this through a telescope, it's going to be all gray. You won't see color. And we can actually talk about why that is. It won't be as clear and obvious, but what you will see is a cluster of stars, and you'll see that this piece of sky looks like it's glowing. And if you spend some time with it, you'll see that there's a bright glow, there's a gap, and then there's like a faint glow around that, right? Looks really cool. Got a really cool design. Some of these nebulae, to a visual amateur telescope of 10 inches or less, are like, yep, it's a smudge. So anytime you can see like neat little characteristics or details, those are cool. And so this one gives you some cool details. I like it. That one's over there. Another great one in that same piece of sky. And I'll tell you what, I'll shut this off real fast to show you a stellarium. So if we move up a little bit, we've got, where is it? Is it 22? No, 22 is a cluster. I want to say it's 18, but for some reason I'm not seeing it. There's M8 is these numbers, by the way. There's a list of objects called the Messier objects. There's like 110 of them. They're really good ones to go after if you're just starting off. And I'm trying to remember the number of the next one I want to show you guys because I really want to say it's 18. It's Messier 18, and it's somewhere in this piece of sky. There's 23. You see, we're all kind of in the vaguely the same area. Well, shoot. Yeah, here it goes. M18. Okay. So this guy is a cluster. Oh, man. I know half the astronomy club. Here it goes. All right. Swan Nebula. Also known as the Omega Nebula. 17. That's what it is. M17. I'm going to look at the chat, and I'm sure it's going to be blowing up with people being like, it's 17. Okay, no, it's not yet. All right. I thought people for sure were going to be calling me on that. So 17. Again, this is a lousy picture. I'll get you a much better picture of this guy. It's called the Omega Nebula. It's also called the Swan Nebula. I think Swan Nebula is the perfect term for it. I like to call it the Rubber Ducky Nebula. But it's a nebula that looks for all the world like a swimming duck or a swan, right? This picture shows it really well. Okay, that picture's tiny. Can I get a better picture that shows it really well? Here we go. Right? You got the body of the duck, his wings here, and his head kind of wraps around like this. Right? Again, the reason why it's called Omega is because all this other stuff, I guess, kind of gives it the appearance of the Greek letter Omega. But really, the part that you can see through an amateur scope... Oh, I don't like this green square here. The part that you can see through an amateur scope looks like it's going to look gray again, right? And it's going to look like a swan. I guess now is a good time to talk about why these objects are going to be gray, right? So when you look through a telescope, the objects you're looking at are very, very faint. Your telescope is guiding that light into your iris, but it's still very faint, right? This is why we want to let our eyes adjust to the darkness. Now, when your eyes adjust to the darkness, you can see more of that faint light, but the retina of your eye is covered in what are called rod cells and cone cells, right? These are the ones that detect light and they tell your brain about it, and you build up a picture. Well, your cone cells can determine the color of light, right? Because each cone cell reacts more to to wavelengths that fall within a certain part of the spectrum. So one set of cones is more sensitive to red, one's more sensitive to blue, one's more sensitive to green. And actually red and green have a lot of overlap, but they're slightly different, right? So your brain figures it out. But they're not very sensitive overall. Light has to actually be decently bright for your cones to even notice it. Faint light that's not bright enough for your cones to see will still activate your rods, but your rods don't know the color. They just know the brightness of the light. So when you're looking at night and you're using your night vision, you're just using rods because your rods are more sensitive. And this is why, like, if you're in like a dark room and your eyes adjust, everything looks gray. You can't tell color, right? You need more light to tell color. So when you look through a telescope, everything looks gray because these objects are too faint for your cones to be able to pick up on the color of the light. Right? That's why, even though these nebulae are all kinds of cool colors and photographs, right? Because your photographic, digital chip or your film or whatever, you can let it gather light over time and figure out the colors, but your eye doesn't really do that. Right? So Richard mentioned some of this stuff like the lagoon and the swan. They even look good in his neighborhood where there's light pollution, right? So a lot of these Messier objects, these M this or M that, are fairly bright examples of these distant faint objects. They're good for getting started. But anyways, that's why things look gray. So you have to temper your expectation a little bit. You're not going to get the Hubble image when you look through a telescope. You're going to get a gray smudge, right? It's going to be sort of gray, going to be kind of blurry. And actually, I can show you that because I can show you. I sketch all of the things I observe, and I sketch them how they look to me. And so you can see what they would actually look like through a telescope rather than what they look like in the images. So if I pull up the same thing, Swan, probably just label it M17. Yeah, okay. Oh, this is a really good one. I got 17 and 18 in the same sketch together, so that's kind of cool. Okay, and now I will show it. Boom. So this is what my sketch looks like, right? So you see there's sort of a vague blurry area, and then there's like a brighter area that's sort of shaped like a duck. That's what you see through a telescope, right? A vague, blurry, gray thing. But it's cool because you know what that vague, blurry, gray thing is, and you saw it with your own eyes, right? It's worth it. But I do sometimes have people that when they look through the telescope, they're unimpressed. And I'm like, you got to temper your expectations, right? You're not going to... I don't have access to the Hubble. This is what you're going to get. Another good example, I'll actually pull up my sketch of M8 as well. That Lagoon Nebula that I mentioned. Because it is... It is also really cool. So M8. Okay, I'm pretty sure I have a sketch of it. Yeah, here we go. Actually, I like this sketch so much. Every year I do another binder for my sketches, and I'll print out one that I really like and make it the cover. This was the cover for my sketch for 2019, I want to say. I just thought it was so cool. So that's what it looked like through my telescope, the Lagoon Nebula I showed you guys earlier, right? Sort of gray, blurry, right? But clearly there's a shape to it. And I also could tell there's a little bit of something going on over here, too. So I sketched that, too, right? I do sort of like stellarium. I let the size of the dot represent the brightness. So these guys are kind of faint over here. These guys are a little bit brighter. Anyhow, this isn't the Dave brags about his sketches show, but I wanted to give you guys that example because one of the cool things about sketching what you observe is it lets you show other people this is what it actually looks like through a telescope. That's one of the things I like about my sketch is I can give a realistic view of what we should expect to see through a telescope rather than if I Google these things, I think it gives an unrealistic expectation. One other really cool object in this piece of sky. Somebody asked, what is the straight line in my drawing of M17 and 18? Oh, so a lot of times I will literally spend like 45 minutes sketching an object, right? It could take a while. This is why Richard gets his observing done quicker than I do. I spend a lot of time sketching. But so during that time, it's not uncommon for me to have a satellite go right through the view. Or I almost said shooting star. We use the term meteor. A meteor will go pew and shoot through the view while I'm looking. And so I indicate everything I observed, right? The point of my log isn't to be a work of art, it's a record. So if that happens, I draw it. I draw a line and I put in my notes what that is. So, and that's one of M17 and 18. If I pull it back up and check my notes, it's a satellite. That one was a satellite that passed through while I was sketching. So I always draw like an arrow to indicate the direction it was going and where it went. And I include those in my sketches. So good question. That's what that was. Another cool thing we could talk about in this piece of sky is M24. Now M24 is cool because it's just, look at all these stars, right? And I'll pull it up in Google. And this one really does look awesome even through like a telescope. M24 star cloud. We call it the star cloud, right? Because it's just like a big cloud of stars, man. It is impressive. I'll show you right here. It's not the greatest photo, but maybe that's working to our advantage because it's more like what you would see. So this is what it looks like. There's like a little patch where there's just a lot more stars, right? The interesting thing about M24, the little Sagittarius star cloud, is that it's not an object, it is a lack of something. And what it's a lack of is none of the space that we have in our Milky Way is actually pure vacuum, right? I mean, the definition of a vacuum is like you could have a whole room and have one atom in it, right? But there's still stuff there. And so the whole galaxy is kind of full of like dust and gas. Places where it's really concentrated, we can see that as like nebulae, right? Little gas clouds and stuff. In places where it's not as concentrated, we can kind of see the stars behind it, right? But it's still there. And so as we look through the disk of the Milky Way, the further stars kind of get lost because their light filters through all that, even that very, very tenuous, low density, practically vacuum on the way to our eyes, right? M24 is a random hole in that stuff. For whatever reason, there's just less of what we call that the interstellar medium, the sort of vague stuff that's between all the stars. That's not enough to be a true nebula, although nebulae I think are considered part of the ISM. But it's just that sort of stuff between the stars that is almost a vacuum but not quite. Well, there's an opening in this piece of space. And so there's actually not any more stars there than there is around it. But this opening just lets us see more. We can see the stars behind those stars, right? Where they would kind of fade over distance because of the interstellar medium. So M24 is really interesting. It's actually a lack of something rather than a something, right? All right. Do we have any other questions in the chat? No, people still hanging out. I'll just keep finding things to talk about. Again, as I'm talking about any topic, feel free to just jump in with questions, clarifications, whatever. And I'm happy to use that because your questions and your topics are the fuel for my fire, right? This is the Planetarium Show. I mentioned this earlier. I'll say it again. This is the Planetarium Show on YouTube where you guys are the Planetarium director. You tell me what we talk about, right? But if no one's mentioning anything, I won't just sit here and stare at the screen. I'm going to talk about something. But I really want you guys to give me the ideas of what we're going to talk about. And you have been. You guys have been a great audience tonight, actually. We've really had a good time. So, and we've got about another half hour left in this thing, too. Boy, time flies when you're hanging out and talking about space. So that's some of the really cool stuff to see over here. Between Sagittarius and Scorpius, we've got a couple other objects here. Again, a few more Mézières. We've got Mézière 7 and Mézière 6. 6 is called the butterfly cluster because it's a star cluster that looks like a butterfly. And you know what? That's actually a good segue to talk about star clusters. So we talked a lot tonight about how stars... Okay, there we go. Planets, actually. We'll talk about planets. Sorry, I'm going to allow myself to get sidetracked because I already have a video on this channel where we talk about the life and death and birth of stars. So let's talk about planets today, right? Let's get the topic onto planets. So we just came off of like a long period of not really having much going on with planets, right? The planets we could see, they kind of went elsewhere. We're going to start to have planets again as we move into August. You'll notice, right, tonight, and my little clock down here is telling me it's like 11 o'clock. So if we want to look at what we'd be seeing, this is like 9 o'clock, right? 10, 11, midnight, right? We've got Saturn and Jupiter coming up. And those are awesome planets. I love Saturn and Jupiter. I'm just looking to see if we got anything else going on. Actually, let me delete the world and see here. We've got Venus and Mercury are hidden. Where is Mars? That's what I'm really looking for is Mars going to be hanging out with us at all tonight? I think not. I think Mars might be on the other side of the sun. You know what? There's a search feature. Why don't I use it? Mars. Planet. Oh, there it is. Yeah. Mars. So this is cool. Mars has been hanging out with Venus lately, right? So if we zoom out a little bit here. If we time travel back a little bit, right? So again, this is like 9:13 tonight. The sun, right as the sun goes down, this is a cool thing to look for. As soon as the sun goes down, I'll delete the constellation lines. Venus will be the first thing to come out. It's going to just be bright as all can be, man. Brighter than bright is. Venus is the brightest planet to the naked eye. It is actually the brightest object in the sky other than the sun and moon. It is really, really bright. So you'll see that the sun will be going down. Sometimes when the sun is even still up, you can see Venus. But as the sun goes down at night, you'll see Venus. As it gradually gets darker, there's a red dot bottom right of Venus, and that's going to be Mars, right? And unfortunately, that's going to settle on it. That's going to set pretty soon tonight, right? 10 o'clock, boom, it's already gone, right? So kind of going to have it till about 10:30, depending on how your horizon looks. Right, so that's Venus and Mars over there. Jupiter and Saturn, if I can move over to the east, I mentioned Jupiter and Saturn, we're going to have to stay up a little bit. So there's like 10:30-ish, we're going to start to see Saturn. Closer to like 11:30-ish, Jupiter is going to come up. Really, around midnight is when they're going to be decently placed to observe. Right? And one thing I want to point out, last year they got really, really close to each other. That was really cool. We had the Great Conjunction. Yeah, somebody was saying early evening for Mars. Somebody else wants more details about Sagittarius A. Cool. Jupiter, Great Red Spot. All right, we'll talk about, since we're on the subject of Jupiter, talk about the red spot. And then I think we'll circle back around and talk a little bit more about Sagittarius A, that black hole I mentioned. Black holes always get people's attention. People love black holes. So, talking about the Great Red Spot, because somebody asked about that. So, Great Red Spot is another fantastic topic. I'm just going to pull up Jupiter, Great Red Spot. Okay, here's a good picture. All right. And there we are. So this is a picture of Jupiter. And Jupiter is what's called a gas giant. The other term we have for gas giants is Jovian, which is a really cool term, and I'll put a pin in that for a second because I do like to talk about that topic. But it's what we call a Jovian planet. Jovian means like Jupiter. So Jupiter, of course, is the example Jovian planet. But the other word, the more common word that we use is gas giant, right? Because they're made of gas and they are huge. They are flipping enormous, right? So this is Jupiter, and it's made entirely out of gas. There may be something in the core, but for the most part, gas. And like slurry of like ice crystals and stuff. You'll see that the surface is all swirly, right? Because it's a big ball of gas. And one thing that you'll notice is there's these little circular objects here and here and right here. Those are storms, right? Jupiter has weather just like the Earth does. I mean, for crying out loud, it's nothing but weather, right? Jupiter is nothing but atmosphere. So it has storms. Well, there's this big red one that sits a little bit below the equator, and that thing is, I mean, Galileo saw it when he first looked at Jupiter. Galileo is the first person to ever see Jupiter through a telescope, and he saw there was a red dot on it, right? He made a note about that. And that red spot is still there today. And what it is it's basically a giant hurricane. So this has really been one of these things that's kind of puzzled scientists. Why is the red spot seemingly so permanent, right? Why would a storm be like a permanent feature of the planet? And I mentioned before that there may be something solid deep down within Jupiter. So some people have speculated maybe there's something down there that's adding heat or energy that's sustaining this thing, right? Keeping it going. A lot of speculation about it. But one thing you'll notice in this picture, and of course if you read this, there's a little bit of a spoiler there. The spot has been shrinking. And this is something really interesting that's been happening lately. If we pull up an older image of Jupiter, actually this I think shows it well. All right, let's see here. This is all 2019. Let me see if I can pull up like a 1970. I'm going to get the Voyager image, right? Voyager Jupiter image. Right? Let's let's see what Jupiter looked like when Voyager visited, right? So the Voyager spacecraft visited Jupiter in, goodness, what was it, like the 80s, 90s? I don't know. I was really little. This is what we saw, right? And you see how wide and football shaped that red spot is, right? This picture is a really good example as well. It's big, huge, swirling, sort of khaki, rust red kind of a thing. Now it's sort of bright red and it's more circular. It's shrunk a bit and it's got a lot of stuff around the outside that's not really part of it, right? It's got this sort of gray coffee color stuff around it. So the red spot has been changing over time. And part of the thought on this is, well, what did we expect? It's a storm, right? It may well be that there is no good reason why this should be permanent and that the red spot will just go away one day. The storm will just burn itself out, and it was just a storm that lasted for several hundred years, and we were fortunate to see it, right? It may be a temporary feature. Others speculate that maybe it shifts and changes over time, right? Again, if there is something deep within the planet that's just fueling this never-ending storm, maybe it can fluctuate but never goes away, right? Maybe the red spot is more permanent. So we just don't know. We really don't know. But it's interesting to see how it has gotten to be like this brighter red, but it has shrunk a little bit. So it is a little bit harder to see in a telescope. Although when you do see it, man, it is like red spot, man. It is obvious. But yeah, what that is, that's a hurricane. And to give you an idea of just how giant this gas giant is, Jupiter it's absolutely huge. Just the spot, at least it used to be when it looked like this, you could fit the planet Earth in it 3 times, right? It's literally a hurricane 3 times the size of the Earth. It's a fun fact I would always throw out at our star parties, except the latest imagery, that's not accurate anymore. It's more like 2 times the size of the Earth, right? But that is, I mean, just an absolutely monstrous hurricane. That's what that is. Now, one of the interesting things, yeah, so Jane says, right, could it be like a volcano? Exactly, like a volcano or a thermal event, something like that could be fueling this spot, right? It could, because again, it maybe Jupiter just has storms that last for hundreds of years, or maybe it is there's something inside that's really fueling this thing. We don't know. That's one of the things we'd like to learn, right? I think it would be cool if we made some kind of like a buoyant spacecraft, right? Like something that could like float in the clouds. Or actually, no, the other way around. I'd like to see something heavy and pressure resistant fall into Jupiter, snapping pictures the whole way down. I'd love to see. The problem is that thing is so huge, like we wouldn't get anywhere near the middle before anything we sent just got annihilated. But if we could figure out a way to make something that could survive the pressure inside that planet and drop it in and let it snap pictures all the way down, I think it would be really cool to find out what's inside Jupiter. Or even if not snapping pictures, even if it's just taking readings, man. Like, I think that would be really, really cool. The problem is Jupiter's so huge, man, that the pressure is just mind-blowing inside of that planet. I think anything we drop in it would get like a third at best and get crushed. Right, but maybe it'd be a cool thing to try if we could. So yeah, so that's an interesting little bit about the GRS. I said I'd put a pin in the term Jovian, so I just think this is a really fun fact. Jove is another name for Jupiter, the Roman god Jupiter, right? So the Romans, they had their gods, right? So Jupiter is basically Zeus. Neptune is Poseidon, right? Mars is Ares, Venus is Aphrodite, Mercury is Hermes, right? And all of our planet names come from the names of those gods. So the Romans sometimes had other names for their gods, like additional names. And another name they had for Jupiter was Jove, right? They sometimes called him Jove. Well, the history behind that is actually really interesting because the Romans basically had this belief that there was like that their gods were definitely real. First of all, everyone thinks their gods are real. The Romans thought their gods were real. But the Romans assumed that their gods were everybody's gods. They didn't think like you have your gods and we have ours. The Romans were like, well, these are the gods, right? So whenever the Romans met other people and heard about their gods, they would try to figure out which gods they were worshiping, right? So like when they met the ancient Germanic peoples and they heard about this Thor guy, they were like, oh, that's Hercules, right? They're worshiping Hercules, right? So they would do that. They would figure out who they thought other people's gods were. So when the Romans encountered the ancient Hebrews, the Hebrews were like, well, no, there's just one. And he's the biggest, and he's the best, and he's the most awesome, and he's the everything god. And the Romans were like, Jupiter. They're worshiping Jupiter, clearly. And so the Romans assumed that they were, they were calling their god, like, to Latinize it, they would call him, like, Yahweh, or however you'd say it, but the Latinized version is, like, Jehovah, right? And so the Romans made that another name for Jupiter. They started calling him Jove. They were like, yeah, Jove, just like you worship, right? And I'm sure the Hebrews were like, not quite. But that's why the term Jove is another name for Jupiter, and why gas giants are called Jovian is because it means like Jupiter. But interestingly enough, you can actually trace the etymology back to like the Abrahamic god, the god of the Hebrews, because the Romans were convinced that that was Jupiter that they were worshiping. I just think that's funny. I just think it's really funny that when the Romans encountered other people, they just always assumed, well, clearly they're worshiping the same gods. They just have different names for them, and that's now become an astronomical term. Right. Somebody wanted to talk a little bit about. Somebody said use one of Jacques Cousteau's submersibles to descend into Jupiter. Again, I know that we have some pretty high pressure in the oceans, but Jupiter's really big. I don't know how high the pressures get, but I would be curious to see how deep one of those subs could go before it goes from being a sub to being a frisbee. I'd love to find out. So Sagittarius A, somebody did ask about that, so I'm going to circle back around to that. Sagittarius A star is what we call, or Sagittarius A or A star is what we call the supermassive black hole in the center of the galaxy. So to quickly recap what a black hole is for any viewers who are not familiar, when a really big star dies, the biggest of the big, the collapse is just unimpeded. There's nothing that will keep it from collapsing, and it just collapses to an infinitely tiny point. And that point has all the same mass and density as the original star, but it's so concentrated that the gravitational pull is insane right next to it. Because gravity, the amount that one object attracts another, is based on mass and area. So if you shrink the mass to zero area, you get maximum gravity, right? You get maximum density, really strong pull. So that's why when you get close to a black hole, not even light can escape. So that's what we call a stellar black hole. It's a black hole left over from a star. Stellar means having to do with a star. So there are also these things called supermassive black holes, which are black holes that contain way more material than one of these stellar black holes would leave. And the first one discovered was in the Milky Way, actually. They noticed that some of the stars in the way middle core were orbiting around an empty spot. There was nothing that we could see there, but the stars would whip around and go back out. And you could tell from the way the stars orbited, you could calculate how much mass must be there. Even though you can't see the object, you can see the effect it has on all the stars. And so they figured out that there is this really massive black hole there. So I'm going to pull up some data on the Sagittarius A star. Oh, that's not a star. That's a star. Right? So let's find out some little stats about it. So let's see here. So the radius is 13.67 million miles. That's the radius of what we call the event horizon. That's the point of no return. Get any closer than that, not even light can get away, right? Nothing comes back. Now it is, let's find the mass. So it is 4.154 times 10 to the 6th power solar masses. So that's a 4,154 and then 3 more digits. So 4.15 million times the mass of the sun, right? For those who don't know. Yeah, someone says Elon Musk. Yeah, Elon Musk could do it. Elon Musk could get something into Jupiter if he really wanted to. So yeah, Sagittarius A star, the supermassive black hole at the center of our galaxy, weighs as much as 4 million suns, all combined, right? It's really huge. There are some much more massive, supermassive black holes out there, as it turns out. But nonetheless, that's massive. Considering that your typical black hole is somewhere like 8 solar masses, to have one that's like 4 million solar masses is outrageous. It's an outrageously huge object, right? Um, Now, the problem with black holes is that we can't see them because they don't allow light to escape, right? We can only see other objects orbiting around them and that kind of thing. Uh, but every so often, material gets sucked into the black hole and it will swirl around it as it falls in, and so it will heat up from the friction of the swirling around and getting accelerated. And what we'll get is you'll have the event horizon where not even light can escape, but just outside that, you'll get a glowing ring of all the stuff falling in, right? And no one had ever been able to take a picture of that, but a few years ago, someone finally did, actually. It wasn't ours. It was actually the supermassive black hole. I'll show you where it is, actually. In Stellarium. Let's go over and find Leo real fast. So there's the Milky... Okay, there's Big Dipper. I'm going to have to time travel a little bit. Okay, here we go. There's Leo. Right, in Virgo. If we add the lines. Leo in Virgo. Leo's a bit more of a winter guy. We don't really have as much Leo right now. He's kind of gone away a little bit. Actually, it's really like a springtime. Springtime's a great time to look at Leo. Between the tip of Leo's tail and Vendomayatrix is something called the Virgo cluster, where there's just an absolute ton of galaxies. And then if we look in the Virgo cluster, we find this chain of galaxies called Markarian's chain. It's so cool, by the way. It's definitely worth pointing a telescope at. And then this guy, M87, Messier 87. Now, Messier 87, if I pull up an image of it, and I know the question was about Sagittarius A star, but I this is related, and it's something I know a little bit more about. Messier 87. Okay. So, pull up the picture here. Okay. So that's Messier 87. And you'll probably notice, first of all, it looks like a big ball of stars. They're sort of blurry, right? This is what we call an elliptical galaxy. So it's not a swirling disk of stars. It's just a blob, a giant blob of stars. It is enormous. It is way bigger than the Milky Way. It's an absolutely monstrous galaxy. And it sort of is like in the middle of the Virgo supercluster, which is the whole clump of galaxies that our galaxy belongs to. One thing you'll notice looking at this picture is there's this blue streak shooting out of it, right? Now, really, all the stuff you see in the blue streak is material that was actually already there, right? The energy shooting out lit up stuff that was already there. So it's not actually throwing material like it looks like. What it is throwing is like X-rays and stuff, right? Just shooting a lot of radiation. So black holes do this when they feed, right? Because all the material is like swirling around the black hole, and the magnetic field of the black hole will accelerate X-rays and things up to the top and the bottom, the north and south pole, just like a magnet has a north and south pole, and it will throw that stuff in these two jets of highly energetic particles out of the two poles, while the rest of the stuff falls into the black hole. And they only do that when stuff is falling in, right? So those jets, that's a giveaway that a black hole is feeding. So that tells us that there's a gigantic black hole inside of that galaxy that is eating right now. Remember how I said that we can only see them if they eat? So there was a group of scientists, they did something called interferometry. They basically got a whole bunch of telescopes to look at a piece of sky, and then they like combined their data and had them act as if they were a telescope the size of Jupiter. It's like a really crazy way you can kind of cheat and have it be like as if it's a bigger telescope. It's really cool. And they basically looked at this thing for like days on end, and they got an image, and the image is startlingly like what we would expect to see too, because this is the picture. No, that's not. That's an artist representation. You have to be careful. Some of these, like that you see, like the really clear-cut lines. It's like this is an artist's impression, right? The actual image is just this guy, right? Looks like a pumpkin spice donut, but that is a black hole. That empty space in the middle there, that's the place where no light can escape. That's why it looks like that. This image is actually taken by, there was a bunch of like light data all around it, and then by like stacking them all up, they were able to subtract the noise from the signal and tease this out. So that's why you still see some light in there, even though it should be absolutely black. You could maybe adjust this in Photoshop and make it look a little bit more correct. But anyway, this is what they got. This is the image they got. And this image is really tiny too. It was like a really tiny image on the actual picture that they had to blow up. So unfortunately, it's not any clearer than this. But you see that glowing ring of material around it. And I've only got 15 minutes left, and I could never do it justice. On YouTube, there's another channel called Veritasium, who has a fantastic video where he explains why it's brighter on one side than the other, what it is that we're really seeing in this picture, because the gravitational pull of the black hole is bending light, right? So not only are you seeing the ring is not just the stuff that's around it, it's taking light behind the black hole and bending it around to the front. So you're actually seeing behind the thing that's in the way. It's really crazy how it works. And he does, like I said, he does a way better job of explaining it. But that is the first and so far only ever image of a black hole. I want to say that same group of guys, that same project, does plan on imaging Sagittarius A star, which I think would be really cool. I'd love to see our own black hole. I think it would be really, really awesome. What's really interesting is that movie Interstellar, I want to say, came out before we got this image, but it was the way they made the black hole look in Interstellar was based on the way scientists predicted a black hole would look. And if you remember in Interstellar, it looks like you see all the material and whatever, and then you see like this arc above it. That's that stuff coming from behind. It's bending. It's actually just a flat disc, but it's bending the light of that disc up so it looks like it's above it. That's what you see here. Like Interstellar actually got it surprisingly close, right? But yeah, that's what this is. So it's really cool. On that, I think I'm going to wrap up a little bit tonight. Jonas says it looks terrifying. Yeah, that is destruction. So, actually, before we go, let's talk about spaghettification, just because I love that it's called spaghettification. So, imagine you're standing on the ground, right? Your feet feel Earth's gravity more than your head, because your feet are closer to the Earth than your head, right? There's something called the inverse square law, which is that gravity gets weaker as you go away. We call it the inverse square law because it drops off as the square of the distance, right? So every 1 unit distance, it's half as much, right? Inverse square. So the further you are from an object, the less gravity you feel, so your feet feel more gravity than your head. But the Earth's gravitational field is sort of a gentle gradient all the way out from the Earth. It's a little bit more gravity near the Earth, but the difference between what your feet feel and your head feel when you're standing straight up is basically negligible, right? Or I'm sitting here on the second story of the house, and one of our roommates is downstairs. Yes, technically he's feeling slightly more gravity than me, but not in any meaningful way. Well, black holes, their gravity gets really intense as you get close, right? If we've charted it out, like Earth's gravitational pull is it's really high, and then it sort of drops off slowly over the distance. Black hole just goes like whoosh, right? It's a huge spike of gravity as you get closer. So as if you were to fall into a black hole, whatever part of your anatomy happens to be closer to the middle than the other is feeling many times more gravity than whatever else. So if you fell feet first into a black hole, hypothetically, your feet, even that small amount of distance from your head to your feet, is enough that your feet are being pulled so much harder than your head that it stretches you lengthwise. And it literally spaghettis you. It stretches you and will rip you apart atom by atom. So what I'm saying is Matthew McConaughey would not have survived. But that's and they literally, in science textbooks, they call this spaghettification. That's the term. So with that, I think I'm going to start wrapping up the show. Thank you guys so much for participating. With the last little bit here, I'm going to make some more announcements for anybody who wasn't here at the beginning when I made these announcements. So, I am part of the Northeast Florida Astronomical Society, also called NEFAS. If you live in the greater Jacksonville area, we are the astronomy club. We are the guys, man. If you're interested in joining our club, I am showing this off to you guys, right? Yes. If you're interested in joining the Northeast Florida Astronomical Society and learning more about what we do, you can always come to nefas.org, nefas.org, and you can become a member by going to membership, join NEFAS, and if it will load for me, fill this out, select your membership level. Students and seniors is $20 a year, individuals $40 a year. These are yearly rates. Families are $50, and then benefactor and corporate is just if you're really generous, you really want to support what we do. These memberships are just for people who want to be part of it, want to be part of what we do and support us. We are a 501c3 nonprofit organization, so all this educational stuff that we do, such as this show, which is actually just something I do. It's not really a club thing necessarily, but also like this Saturday when we go to Hannah Park, or this Saturday when we go to Mosh. Unfortunately, we're doing both at the same time. You got to pick which one you're going to go to. We don't charge for any of that. Now, those venues may charge. Mosh is charging $25 a person to attend that cool concert that they're having. That's because that's the point. Mosh is putting on a concert for money. That's their prerogative. We're volunteering there. Hannah Park charges $5 a head to get into the park, but we don't charge once you're in there for our thing, our astronomy thing, right? When we show up at like schools and stuff, we don't charge people, right? Sometimes organizations will pay us to come out and do it, but we don't charge the people who attend. That's free. You join NEFAS because you want to be a part of the club and you want to be part of an astronomy community because you have a telescope or whatever and you want to learn more about how to use it and be part of a group of guys. You want to support us. That's the reason to join. But I'm not a salesman. I'm always upfront with people. We are a non-profit, so all of our stuff is free. You don't have to join to attend these talks. You don't have to join to attend Hannah or whatever. If you are interested in joining, though, that right there I mentioned. And you can also, if you just have questions, you can go right here, NEFAS BOD. That's the board of directors. And here I am. So you can click this link and you can email me. And I respond to my email inbox as well if anyone has any questions about the club or about astronomy. I'm happy to help out with astronomy stuff. That's not necessarily club stuff as well. I also want to give a shout out. I forgot to do this at the beginning of the call of the presentation, but in St. Augustine, there is also a club called Ancient City Astronomy Club. Their website's down, or I would show it to you, but they're called the Ancient City Astronomy Club, and they're an awesome group of guys. So if you live in the St. Augustine area, I recommend getting involved with them. I'm actually a dues-paying member of both clubs because I really believe in the educational outreach and things that both clubs do, and I want to make that possible. So that's why I'm a member. And like I said, I'm the membership director for NEFAS, so wouldn't be doing my job if I didn't at least let you guys know you can join the club. And yeah, I mentioned this Saturday we're going to be at Mosh. Doors at 7:30, concert at 8:30. $25 to attend the show. I'm not sure if you have to pay to just hang out and like do the astronomy stuff, but I think it's really about the show. So I think if you're coming, it's $25 to come to the whole thing. We're going to be there with telescopes. I'm going to be there personally, so if it's clear, I'm going to do my laser pointer tour, and we're going to look through telescopes and whatever there as well. And there's going to be a really cool concert I keep mentioning because there's this band called Skyview. They do like astronomy music. It's pretty awesome. They're going to be in the planetarium. Also on Saturday is our Hannah Park observing session. Normally I would be there, but I'm going to be at the Mosh. But this is our first time doing Hannah Park since the pandemic, and so we do it every month near the first quarter moon, right? So we can look at the moon, among other things. And so we're going to be set up in Lot 8 of Hannah Park. The gates are going to close at 7:30, and they will not open again. So if you leave, you can't come back in. So if you want to attend, you must be there before 7:30. You can't be fashionably late, or the gate will be locked. But starting at sundown, it's like 8:30ish or something. So when you get there, hang out for a bit. You're gonna have to wait for the sun to go down for like an hour. Sorry to say, but once it does, there's going to be
Normally, I would do my sky tour at the Hannah Park, but I won't be there. But there will be a lot of guys there with their telescopes who will be more than happy to talk about equipment, talk about space, and show you the planets and all the cool stuff like I mentioned. So those are, sorry, allergies, man. Those are a couple of cool events we have coming up this weekend as well. So as we start to do more of that in person stuff, I'll be sure to shout those out on this. Uh, I guess this is not a podcast, a vlog, whatever this is. Um, so these presentations, I guess. So that's just about it. We've got like 6 minutes left, but I don't know if there was anything else I wanted to talk about. Starting to get a little bit tired. This just kind of takes it out of me talking for 2 hours straight. Who am I kidding? I can definitely talk for 2 hours straight. But I'll just go ahead and end it 5 minutes early, I guess. Thank you guys so much for hanging out and having a good time. Feel free to stick around in the chat for another 5 minutes if you want to. I'm going to go ahead and throw up the end card, and thank you so much.